When a go-kart changes direction, it's the adhesion between the tyres and the road that makes it follow the new line of the steered wheels. But the faster a kart travels, the greater its forward momentum. This can present problems when trying to take a corner too fast. The forward momentum can prove too much for the tyres, so that the kart tries to go straight on. The result? The tyres lose grip and the kart spins. Although these adhesive forces act at road level, the kart's momentum acts through its centre of gravity, the centre point of both the kart's and the driver's weight. This is much higher than at road level. On corners, this tug-of-war results in a pivoting force that can threaten to turn the kart over, which is why the kart driver will lean into each corner to try and shift his centre of gravity. With a car, the forces involved are the same, although the suspension changes things slightly. When going round a bend, the pivoting force just described acts on the body, but the suspension allows it to roll while still keeping the wheels firmly on the ground. Generally, designers try to limit this roll, which apart from anything else is uncomfortable and worrying to those inside.
Most manufacturers fit a strong bar, the anti-roll bar, to the front of the car. It's fixed to the suspension at each end, and then is clamped to the body in such a way that it can swivel in flexible bushes. This means that when both sides of the body rise or fall together on the suspension, as when the car goes over a road hump, for instance, the bar comes under no tension and simply swivels.
On the road, when the car goes into a bend and the body starts to roll, one end of the bar is forced up as the other is forced down. The bar twists. But the bar, being spring steel, resists this twisting action and in so doing limits the body roll. Some cars have an anti-roll bar at the rear as well. Another problem for the designer is how to keep the body level and at a constant height, both when there's just a driver on board and when the vehicle's fully laden. Each spring naturally tends to compress a different amount, depending on how much body weight it's taking. Without some form of compensating device, the rear suspension on a loaded car can compress quite alarmingly. This restricts the spring's ability to absorb further shocks, and at night it can leave the headlights picking out the treetops rather than the road itself. One solution to this problem is to use self-leveling dampers. There are various types. One is the Nivomat design. If the rear of the car is heavily laden and the springs and dampers therefore highly compressed, the dampers will use the impetus given by the bumps in the road to pump themselves up. This raises the rear of the car to its normal ride height, leaving the dampers still able to do their main job. Another self-leveling system dispenses with springs altogether. On Citroën's hydropneumatic suspension, the springing effect itself, rather than just the damping, is provided by gas compression. It's rather like an airbed replacing a conventional sprung mattress. Each wheel is sprung independently. As one is forced up by a bump in the road, a piston is pushed via a special fluid against a diaphragm in a spherical container. Behind the diaphragm is compressed nitrogen. The piston forces the diaphragm up, compressing the nitrogen even more, so absorbing the shock. It's self-leveling because if the body sinks too low, a valve is opened which allows more of the fluid into the sphere from a central pressurized reservoir, and the body rises again. A classic example of a linked suspension is the Citroën 2CV. Here, a level ride is achieved by linking the front left suspension with the rear left, and the front right with the rear right. The linkage is via a horizontal coil spring and dampers each side of the car. When the front wheel is forced up by a bump, the spring expands, so applying a counteracting downward pressure to the linked rear wheel. The effect is such that although the body rises up and down, it actually stays level. It doesn't pitch, doesn't rock backwards and forwards. The system also helps to level the body when heavily laden. Yet another ingenious suspension system is adaptive damping. Here, after the system has been switched on by the driver, the dampers switch automatically from soft for comfort to firm for precise handling, and back again as required. As these two cars demonstrate under test conditions, when accelerated, a car on soft dampers will naturally sink on its suspension. Adaptive damping will automatically switch to a firm setting to control this. On corners, a car with soft dampers rolls. Adaptive damping switches automatically to firm to limit the roll. And if a hump in the road is taken too fast, a car with soft damping lifts on its suspension. This can make it difficult to control when it comes down the other side. Adaptive damping senses the car lift, switches to firm, so the lift is limited. The driver has precise handling as the car comes off the hump. Under braking, a car with soft damping dives. Adaptive damping will switch to firm to control that dive.
Outwardly, on Ford's Mondeo, the adaptive dampers look like standard McPherson struts with their coil springs and integral dampers. However, at the bottom of each is a small solenoid valve. With the valve closed, the damper's natural setting is firm. But when the solenoid is powered, it opens a small valve that allows fluid from the inner chamber to pass the damper piston more easily. This creates the damper's soft setting. Switching between the soft and firm settings, the effect of controlling the current to the solenoid, is handled by the adaptive damping electronic module. On Mondeo, this is housed in the boot. If the adaptive damping is switched on by the driver, the module initially sets the dampers to soft, but it also monitors key systems in the car, one being the steering. A sharp turn of the wheel, and the sensor on the steering column sends a signal to the module. Another sensor monitors the brake pedal. A third monitors the throttle plate, sending a signal when the accelerator is opened sharply. A fourth sensor is contained in the module itself, monitoring the car's up and down motion. If one of these sensors detects a movement that is outside preset limits, the module will immediately switch off the current being sent to the solenoid valve. The valve closes, and the damper switches to its firm setting in just a fraction of a second.
Although wheels and tyres aren't usually thought of as being part of a car's suspension, they have a great effect on how a car handles and rides on the road. They must be strong, light, well balanced and capable of absorbing some stresses while resisting others. Conventionally, wheels are made of pressed steel, but aluminium or magnesium alloy wheels are increasingly popular. These are so light and strong that they can be made much wider and so can carry much wider tyres. With more rubber in contact with the road, these produce greater adhesion, though admittedly at the expense of slightly heavier steering and slightly greater fuel consumption. But there's more to a tyre than just its size. A key requirement is that it must compress easily to help absorb road shocks. On corners, it must be strong enough to withstand enormous sideways stresses. There are two main types of tyre: radials and the older cross-plies, which are becoming less and less common. The difference between the two is structural. Cross-ply tyre walls are quite stiff, which means that if the tyre is at an angle to the road, or when it's under particular sideways stress, part of its tread may lift off the ground. The tyre walls are stiff because of the way layers of webbing or plies are arranged beneath the outer rubber casing. They run diagonally across the circumference of the tyre, and so are called cross-plies. Radials have more flexible side walls, which absorb sideways stresses and bend, so that the whole width of the tyre stays in contact with the road. This feature is again due to the tyre's inner structure. Here, the main webbing plies are arranged radially, so helping to create the tyre's flexible characteristics, and prompting the name radial ply. Finally, the tyre's tread, the pattern of channels cut into its surface, is vital for driving in the wet. Wet roads present a potential danger to a driver because of the possibility of a film of water building up between the tyres and the road surface. The channels cut into the tyre collect the water, allowing the uncut sections to stay in contact with the road. The water is then thrown out behind the tyre. This can be graphically illustrated by showing how badly worn tyres, with little or no visible tread, behave on a wet road. mini wall of water builds up immediately in front of the tyre. Eventually, the tyre is riding on a film of water. The tyre starts to aquaplane, a highly dangerous state if the driver has to brake or steer sharply. It's vital that the correct size and type of tyre is fitted. Manufacturers now specify tyres for their vehicles. Identification codes are moulded into the side wall of every tyre. The 3-digit number is the tyre's width in millimetres. Then there may be a 2-digit number, which is the depth or profile of the tyre, expressed as a percentage of the tyre's width. Then in this case there's a letter, Z, which refers to the maximum recommended speed for the tyre. In every case there's another letter referring to the tyre's construction, usually these days R for radial. Then there are 2 digits which refer in inches to the diameter of the wheel where the tyre sits. On many tyres, the speed code letter is actually given at the end instead. Here it's T, usually after yet another figure indicating the tyre's maximum permitted load. Finally, the balance of wheel and tyre is important. The tyre may have left the factory with one part fractionally thicker and so heavier than the rest. This imbalance can cause alarming vibrations and affect steering control. The solution is to clip small slugs of lead to the wheel to restore balance.
Routine service to the modern suspension system really is a thing of the past. Occasionally, after high mileage and heavy use, the dampers may become ineffective, but replacement is not a major operation. Also susceptible to wear are the various rubber bushes used to mount suspension components to the body. They not only provide a flexible mounting, but also help reduce road noise. Again, replacement is fairly straightforward. But one set of components needs regular attention, and mainly from the vehicle owner: the tyres. All car handbooks contain details of the recommended tyre pressures. If tyres are not checked regularly, sometimes as often as once a week if a vehicle covers a high mileage, they can deflate. A difference in pressure between the 2 front tyres, even of a few pounds per square inch, can make the steering pull to the side where the tyre is softest. Under braking, that pull can be quite dramatic. Another problem with an underinflated tyre is that the tread channels close up. If the road's wet, this can easily lead to aquaplaning. When a vehicle's heavily loaded, tyre pressures should be increased to avoid creating the effect of underinflated tyres. Most handbooks contain details of these higher recommended pressures. And the other thing owners should keep an eye on is tread depth. In most countries there's now a legal minimum. There are usually bands or small areas of tread that are designed to wear smooth, as a warning that the rest of the tread has almost reached its minimum depth.
In the 11th unit of this series, we'll find that a system which is simple in principle, steering, can in practice be surprisingly complex. We'll look at the most common steering system, the rack and pinion, and the steering box found on commercial vehicles, before looking at a number of subtle but crucial design factors. Factors such as slip angle, toe in and toe out, and camber and caster angles. We'll discover what is meant by oversteer and understeer, before finally looking at power-assisted steering.